So in this lecture series, we shall learn how we can model a basic plate girder arrangement. So plate girders are nothing but the simple this type of I-shaped sections, which are extensively used when the span of the loading is quite high. So that is why they are mostly used in bridges also. In addition, sometimes it do happens that we may use them in the buildings also. So plate girders are basically explained in this separate PDF also by NPTEL. So they become popular in the late 1800s when they were used in the construction of railroad bridges. And basically the main girders that is require web stiffening, either transverse or both transverse and longitudinal, to increase efficiency. So in this lectures, you can see in this picture, you can see some various vertical stiffeners. So these vertical stiffeners are used to increase the efficiency and to basically stiffen the web. In this I section here, this is the web and this is the flange. So a simple I shape shall have two flanges and one web. This is nothing but cross girder that we are looking here, and this is the cross bracing. So sometimes the variation of bending moments in main girder may require variation in the flange thickness to obtain economical design. So basically what happens when we are watching a simple plate girder. So in this plate girder, for example, the maximum bending moment in this area here. So the bending moment profile shall be WL square by 8. That is why we usually consider the equivalent UDL, and on that UDL we calculate the bending moment here as WL square by 8. So bending moment at this point is 0 and the bending moment at the center is the maximum here. So the designer practices that we increase the flange thickness in this area and we decrease the flange thickness in this area. So that is what this lecture is saying here. And these are various thumb rules for the highway bridges and railway bridges, that how we can predict the web thickness, flange width and overall depth. So this is a simple plate girder bridges. So this type of plate girder bridges is seldom used, that is not used, but this type of plate girder bridges are mostly used in the railways as well as in the highways. So what basically you are watching here is that these are the two plate girders and they are tied by the bracing. So why we are providing bracing here? Because the when the heavy loading comes on the top of this type of arrangement here, the eccentricities do come. So to make this whole system strong along the minor axis also, we do provide this cross bracing. And it is a standard practice that we do provide the closing girders or the cross girders at the starting point as well as in the end point. So this is not only for the steel structures. This type of practice is also used in the RCC structures also. So in RCC structures, what we do is that we do provide three cross girders, one at the starting point, one at the end point and one in the in between. So the BS 5400, although this is a very old code, so BS 5400 covers the design of the plate girders. AASHTO provides a separate guidelines. AISC 360 also provides a separate guidelines. IS 800 Indian standards also provide a separate guidelines. EC3 European code also provides a separate guidelines for the design of the plate girders. So this is basically the flange, top flange, bottom flange and the web. And our practice is always that we should restrict our section to the compact section. So either it can be plastic or compact. It should not be semi-compact or slender sections. This is the simple formula for the bending moment capacity, that is ZP into Fi divided by gamma m. So ZP is nothing but plastic section modulus, Fi is the yield strength and gamma m is the material safety factor, that is 1.1 for the structural steel, 1.15. So we do provide, we do cross check that whether the plate girder is safe in the lateral torsional buckling or not. Web buckling is also a very important phenomenon that needs to be checked in the plate girder design. This is basically the plate girder, and here you can see that this is when the section rotates like this, this is the view showing the lateral torsional buckling. That is, this part is rotating like this and this part is rotating like this. So it is just like when we dry a cloth and rotate that cloth. So in that particular sense, when the steel girder rotates, this is called the lateral torsional buckling. This is the shear moment interaction diagram for a simple plate girder. So why we provide this lateral bracing for plate girders in that to avoid this lateral torsional buckling and distortional buckling. These are some examples of plate girder bridges. So here you can see that the plate girders are provided from end to end, and the practice is that we do provide the splicing on this point here. We never provide splicing at the midpoint, because at the bend point the bending moment is the maximum. So it's always like good tendency to provide the splicing joints at the areas where the bending moments are negligible or minimum. So I hope the things are now clear to you, that how a plate girders looks like, how and what are the various uses of that plate girder. So in the next lecture I shall teach you about the basic arrangement of the plate girder, how you can model a simple plate girder arrangement in the StartPro software, and how you can analyze and design it as per the various design standards. So basically plate girders are most of the times used in the bridges, and due to the short length of this lecture I cannot teach you about the various type of loadings that OSTO provides or IRC, that is Indian Road Congress, provides, but I shall teach you how we can check the plate girder for a particular UDL and how we can design it. So in this lecture we shall try to model a small arrangement of this type of plate girders. So we can go to our start model here, and in the editor file we can enter units as meter and kilonewton and join coordinates as 1, 0, 0 and 0. So we can let us say if we want to design a girder with 16 meter length, so we can press X as 16 meters here, and we can join this from first node to second node. We can check that the length of this beam is, or girder, is approximately 16 meters. So similarly we can Control C, Control V again, and Z we can select it as, let us say, 4 meters. And we can insert nodes in both of these girders. So we can, let us say, add N as 4 points and left click on OK. So we can divide it into 3.2 meters span. We can draw a beam here, and we can left click on insert node and left click on add midpoint. So if we want to draw this type of bracing here, so how we can draw this type of bracing is another very important concept. That is how we can tweak the specifications option in the start software to make it somewhat look like this, because right now this whole arrangement will look like this. So what we can do, we can go to specification, or before that we can go to properties and we can go to define. We can go to tapered eye. Depth of section start node we can enter it as 1.2 meters. Thickness of web we can enter 0.012. Depth of section at node 1.2 meter. Width of top flange we can enter it as 0.6. Thickness of flange we can enter it as 0.040. Width of bottom flange again 0.6 and 0.032. So I have taken the thickness of top flange is 40 mm and thickness of bottom flange is 32 mm. Left click on add here, and we can select both of these sections here. So if we check this in the 3D view, so here we can see that these are the two main plate girders here, and after that this arrangement, this angular arrangement is usually most of the time of double angle system. So we can, what we can do here is that we can go to section database here. We can left click on this British sections, and we can select angle, angle we can select it as UA 100, 110 and left click on add here. So we can select this arrangement here, and after that what we can do, we can go to specifications, left click on this beam here, and then we can left click on offset, location is start and Y as 0.6 meter here, and then again beam and offset and Y as 0.6 meters again. So we can assign this part here, and again we can assign this part here. So let us check that whether this arrangement is correct or not. So this half arrangement is correct, but to make it more clear, what we can do, we can again model this beam here, and we can left click on beam, offset, start, Y as minus 0.6, location end as Y as minus 0.6. So if we check this type of arrangement in the 3D view here, before that we do need to assign the property also. So if we check this arrangement in the 3D view, here we can see that now this arrangement has been joined correctly. So we can say that this type of cross arrangement is now correct, except for this top tie and bottom tie is missing. So what we can do here is that we can again draw a beam from this point to this point and select this beam. We can again go to the specifications, and we can enter start as 0.6 and end as 0.6. After that again we can draw a beam here, and again we can enter start as minus 0.6 and end as minus 0.6 in the vertical direction. And if we check now we check this whole arrangement in the 3D view, we can take it as double angle here. So now this arrangement is correct and is matching as per this arrangement here. So these type of hacks are like known by very less people, so it do helps in achieving what basically shall be modeled or what basically shall be done when we are doing the practical design. So after that what we can do, we can select this whole arrangement here and left click on translation repeat along X, spacing we can select it as 3.2 and left click on OK here. So similarly we do need to do the process again here. That is, we again need to add the midpoints here. Left click on insert node and add midpoint, and then after that we again need to select all the beams here, go to the specifications and start vertical 0.6 and end as plus 0.6. So again we do need to model this beam arrangement here. We can take it as start as minus 0.6 and end as minus 0.6. After that, we can again model the horizontal beams. We can take it as start plus 0.6 and end as minus 0 plus 0.6, and then again we can model the beams. And then again we can select start as minus 0.6 and end as minus 0.6. So we can select by missing attributes and missing properties. Go to view and select objects only. We can go to the property section here and just assign double angle to all the sections here. The section on which the properties does not properties had not been assigned. So now we can see that this whole arrangement is now correct. So now we have drawn a simple plate girder arrangement, and if required, what we can do here, go to the geometry, move, joint, Z as 1 meter, and left click on retain connections. So after that, we need to go to the load and definition option, and here we need to enter one as dead load and the other as live load. For dead load, we can first of all take the self weight. We can take it as minus 1.1 here. After that, we can enter the UDL also. So dead load and member load. Here we can enter, let us say we want the UDL to be minus 6 kN per meter. So we can go to select beams parallel to X, and we can select this minus 6 kN per meter UDL to both of these beams. After that, let us say we want the live load to be of some higher value. So we can, let us say we want it to be minus 75 kN per meter. So we can go to select beams parallel to X axis, left click on assign to selected beams, and yes. So now both dead load and live load has been selected, and after that what we need to do here is that we can go to auto load combinations or define combinations. We can select both of these combinations here, and we can enter 1.2 as dead load and 1.6 as live load, the typical load combination for this American codes. So we can check it for 1.2 dead load plus 1.6 times live load, and left click on add here. And after that we can go to analysis and add. After that we can go to design. Before that we need to go to the support area also. So we can go to left click on create. On one end we can create this roller connection. So we can go to fixed butt, and we can release everything except FY. So this is just like a point where only vertical reactions shall be there. And on the other end, what we need to do is that we can release all the bending moments here, and we can have Fx, Fy, Fz on all of these 3 points. So we can select both of these points here. And after that, what we can do is that we can go to design. Analysis command has already been given here. After we can go to design and select steel. We can select AISC 36010. We can left click on define parameters. So here we can select the properties or specifications also. So we can select ultimate tensile strength and yield strength. So we can select 310 can select LZ as 16 meters here. Mean we can enter here as 200. Method we can select LRFD. Stiffness we can select it as, let us say, 0.75 meters. We can also select UNB and UNT. So UNB we can select it as 3.2 meters because we are supporting the top and bottom flange with the help of bracings. So that is why we can enter UNB and UNT as 3.2 meters. So FILD 310 can be assigned to the whole view. LZ we can assign it to the plate girders here. Similarly we can select the main 200. Stiffener we again from 1 to 10. UNB again 1 to 10, and UNT also again 1 to 10. After that we can go to commands and after connect check code and takeoff. The steel takeoff we can assign to the whole view, and check code also we can assign to the whole view. And in addition to that, what I want to show you is that we can also assign the horizontal loadings also. So we can go to the nodal load. FZ we can select, let us say, very small values of 10 kilonewton, let us say, that is 1 ton. So we can select all the joints here. Can decrease the value of this FZ. Let us say we only want it for 2.5 kilonewton. So after that, let us analyze and check the structure, that whether the whole arrangement is correct or not. So here we can see the ratio as 0.552, and before that we can check the output file also. So these warnings you can ignore, that this 42 and 37 are between the same nodes, because when we draw this type of arrangement in the plate girder section, so these type of things do happen, but you can ignore these warnings. And let us see the bending moment diagrams here. So if we select this MZ here, and we can check it for this 1.2 times dead load plus live load. So here you can see that this is the simple WL square bed bending moment diagram that has been shown here. So let us do some various permutation and combinations. That let us suppose our plate girder is of this size only, that is 1.2 by 600. So here we can check that the maximum bending moment that it can cater is 7948.5 against 4280. So still we have some capacity. So if we want to increase the live load, let us say we want to check it for 100 kN per meter UDL. So we can go to our loading and change the values here, and still you can see that only 71% is the utilization. So let us increase it to be to the value of 125 kN per meter. So now the ratio is good, that is up to 0.88%. So it can easily cater the loading of 125 plus 6, that is 131 kilonewton per meter UDL for this type of plate girder arrangement. And if we want to see the this bracing arrangement here you can see the simple MY and FX values. And here we can see that the ratio of this is only 70%, and the ratio of this girder here is approximately 80%. So this is basically a single girder only from this point to this point. But due to the bending moment profile, so due to this bending moment profile, this maximum bending moment is around here, and the minimum bending moment, that is 0, is at the support sections. And if you want to see the FX here, so here we can see the FX arrangement also. This is the FY, that is shear arrangement. So as this we had studied in the college also, for simple UDL type of loading, this is the perfect shear arrangement here. And this is the torsion. So torsion is almost negligible here. This is the minor axis bending moment. This is the major axis bending moment. These are the beam stressors, and this is the deflection. And if you want to check the deflection for our plate girder, we can go to displacement and summary. So here we can see that for for limit state, that is 1.2 times dead load, 1.6 times live load, the deflection is approximately 59 mm. And although the deflection is always checked in the service load combination, not in the limit load combination.